Okay, today we're gonna start chapter 8. So it's the application of anti-differentiation. This time what we're gonna do is narrow it down to actually determining the area of a curve below the curve to the x-axis. So that's the application of integrals, is to find the areas of various shapes. Okay. With 8a, we start with the fundamental theorem of calculus. So you need to have a function to be continuous on an interval a to b. A is less than b. If we define capital F as the indefinite integral of f, which we have done in the previous chapter, it's the integral plus a constant. You will use the indefinite one, so you don't have to worry about the plus c. You will define as, that's the notation, so it's integral of f of x in terms of x from a to b. It is defined as equal the capital F of b minus capital F of a. So you start with a and you finish at b. So when you do the difference, it's from b minus f of a. So the order matters. Okay. We can also define that integral, even if we know the boundaries, we can add an additional parameter. So here we're going to define f as continuous on an open interval. A is a value of that interval, and capital F of x will be defined. So we're looking at defining that integral, so we call it capital F of x, and that variable is going to be that upper limit of the integral from starting from a. And not to confuse the two variables, when we anti-differentiate, we just introduce a t variable, so it's a temporary substitution. We could have called it u, v, any other letters but x. So when you anti-differentiate that and you use that that notation, that's going to be in terms of x. Correct. Sorry, I finished with year 11, so I've covered 9h. Okay. So the notation here is, if I differentiate that, which is the derivative of that, that cancels out with this one. That will be the definition of f, lowercase f, and both of them will be in terms of x. Okay. So just to clarify, so this is from the fundamental theorem of calculus. To get that second point, what you could do is something like this, just to make things a bit clearer. So let me change blue. So here, that upper limit, if we change that to so you will change that t. Okay, that upper limit, you call it kx, and that will be an x. So it will be f, capital F of x minus f of a. That will be a constant, but that doesn't really matter. We can call that's a constant. That will be the definition of that integral. So that lower limit is a and that upper limit is x. Okay. Then you will have properties of integrals. So if you have a definite integral from a to b, you can introduce another parameter, so we call it c. Usually c will be between a and b, but actually it doesn't really matter. The integral being an algebraic amount, it's not an absolute value. It can be negative as well. So c can be anything out of that interval, as long as when you break it, you separate it. As long as that function f is continuous between that interval and that one, it's still applicable. With the definite integral, if the start and the end are the same, is equal to 0. Okay. If you have an integral and you have a constant factor, you can just makes your calculation easier. If you want, you can take that constant and factorize it outside your integral. Okay. Also, to do your integration, so let's say you have a polynomial expression, you can separate your polynomials into separate integrals when in each integral you have the separate terms. Okay, so if you add them or subtract them, it's equal to the sum or the difference of the integrals. Okay, last one, also as important as the others, is you can change the sign of the integral by simply swapping around the boundaries. So here the boundaries is start from A up to B. If you swap A and B, so from B to A, it's actually equal to the opposite. Okay, now that equality is actually related to that one, and an easy way to do that is actually no, forget it, that's fine. No, I don't want to confuse you, so leave it as that. Those are the properties that you need to know. Again, have them in your notes. It's a good idea as you practice them. It's always good to have that to memorize them. You'll become more efficient if you remember those rules. So if you have, for example, the last rule, which is kind of useful in for certain type of questions, if you don't have that in the back of your mind and you haven't read your note at the time, you might not get the idea to use that strategy to simplify your integral. Okay. Alright, a few examples I'm going to go through. First one, so you have a function given like that. Now notice it's an even function. Very important to have an idea when a function is even or odd. If a function is even and we're looking for the area, now notice when it says the area is actually you're looking for the integral that is positive. So if by a section of the integral becomes negative, you need to flip the sign to determine the area, because if you add two integrals and one is negative, by cancelling each other out, you're actually not calculating the area. Okay, so basically the area is the modulus of your integral, if that makes sense. Okay, and that will be the application when you use the CAS calculator. You can do your quickly a verification using a CAS calculator. When you want to find the area, when you define your integral, you just add the modulus to help you out. So here you define the area. So you have your the area is going from -1 to 1. So that is your area. But again, as I said, it's an even function. So there is a symmetry, meaning that from the left hand side to the right hand side, -1 is a symmetry from 1. So if we take just that right hand side and we double it, that will also be equal to the area. Okay, so that will be twice the area from 0 to 1. That again, you need to remember that is the inverse function. So here there's a 2 squared. Okay, now to anti-differentiate, you must have a 2 here. It means you need to divide no, sorry, let me rephrase that. The way you need to have a 1 here. So what you will need to do is actually you need to factorize a 4. That will be x squared over 4, or x over 2. Okay, and we take that 4 out of let me add the working out somewhere, because I think it's not that clear. Let me get a pen. use that space here. So on the denominator, what you do is you factorize a 4 under the square root. That gives you 1 minus bracket, it's x squared over 4, but the 4 I can bring it inside the bracket, that will be x over 2 squared. Okay, now that 4 we can, that's dx, 1 times dx. That 4 we take it, we factorize it, so the square root of 4 is a 2. So what you end up with is the 1 over 2, that's square root of 4, I'm going to bring it on top, that's going to be a 1 over 2, square root of 1 minus x over 2 squared. Now inside the x over 2, that 1 over 2 is the same value as, that 2, how does it work out? Yeah, that's the same value as over here. So now you can anti-differentiate using inverse of sine of x over 2. Okay, the boundaries would be from 0 to 1. So here, that's what the square bracket represent, and you can substitute the square bracket by, it's the difference of inverse of sine of 1 over 2 minus inverse of sine of 0 over 2. Okay, brackets again. Now that's 0, so that's simplified. They add another, they jump some steps. They forgot some of the working out. So that your inverse of sine of 1 over 2 is pi on 6, so that gives you pi on 3 as your final answer. That's your area. Something to add, if you were to do that on an exam paper, it's a good idea to always write square units. Even if it doesn't tell you the measurements in terms of distance, like meters or kilometers, by writing square units, you are aware that it is in an area that you are calculating. Okay. Alright, following example 2. You have another function, it tells you the interval from negative 2 to 2. Even without the graph, if you do a substitution with negative x, you'll find out this function is even. So being even, if we wanted to find the area, due to symmetry, we can just take half of it from 0 to 2 and double it, and it will give you the whole area that is shaded in yellow. Okay, so here is your area as a function. Here, because you have a 4 on the denominator, it relates to arctangent of x over a. Here that's your a squared, so we need to introduce a on top here, and if that's a squared, a is equal to 2, we need to introduce a 2 here, and the way you introduce a 2 is you divide by 2 as well. Okay, then you use the symmetry, so it's from 0 to 2, that's your arctangent of x over 2, you substitute 2 and 0. Arctangent of 0 is going to be 0, so there's a minus here, a term that is not, it is 0, and inverse tangent of 1 is pi on 4, and that gives you 3 pi on 2 square units. Okay, okay. Most commonly you will have a question, it's a worded question without the graph. So if you have a CAS calculator, graph the function to get an idea. Make sure you zoom out, you move your window to make sure you include all the required, the positive function, negative function, the identify your intercepts. Okay, so here you have this sketch of f. So the domain is from -1/2 to 1/2. The reason why the domain is like that, usually for inverse of sine is from -1 to 1, but because you have a 2, the period is changing, so that's going to be from that, you reducing the domain accordingly. You need to shade the region defined by the inequality, so x has to be between 0 and a half, and you need to find between f, so y has to be between 0 and f, so it's actually, it tells you it's below the curve of the function f. So from 0 to a half, so you look on your x-axis is from 0 to a half, and y has to be between 0 and f, so it has to be above the x-axis and it has to be below the function, so that's what you shade in yellow here. Okay, alright, so that is what you need to figure it out. There's an annotation, so the antiderivative of inverse of psi is not required for this course, but the area can still be determined as follow. So what you would do, and this is a trick, so you can see, if you see that rectangle here, now that area is what is defined as the inverse function. So at the way it is, algebraically you're not able to calculate that. So this is a trick that is important. If you look at an integral and you can't anti-differentiate, what you need to do is refer to the curve. So if you swap around the x and y axis and you look at the area of the curve to the y axis, that section in blue is actually now the inverse function, of inverse of sine. So what you need to do is determine this one. So you have y equals inverse function of 2x, you swap around the x and y and you make the new y the subject, and you end up with half of sine of y. The boundaries now will be from 0 to pound 2. So what you need to do is you look at the endpoint. So when you substitute x equals 1, that endpoint has a y coordinate of pound 2. So from 0 to pound 2 will be the boundary of that new integral. So now you anti-differentiate from along y. So that's a function in terms of y. The area of a rectangle, it's easy. It's a half times pi on 2. So that gives you pi on 4. You anti-differentiate your sine in terms of y. That gives you negative cos of y. From 0 to pi on 2, you substitute and that gives you your answer. Okay, so again, when you have a function that you can't anti-differentiate, think about, can I use the inverse function of what's given here and anti-differentiate? If it works, then you use that rectangle method. So you do, the area of a rectangle will be the sum of the two areas, so the antiderivative of the function plus the antiderivative of its inverse function. Okay, example 5. So again, you have another function. Find the area of the shaded region. Now notice the function is negative, it's below the x-axis, so when you anti-differentiate, your integral will be negative, which is fine, it's supposed to be negative, but then to find the area you just flip the sign or take the modulus of it. Alright, so the way they did it, they had the integral, it's from pi on 2 to 3 pi on 2, those are the intercepts, they are annotated from the function, and they added a negative. Okay, Now when you have a circular function, the power is odd, you go back to one of the technique, you factorize a linear factor, which is a cos. You have a cos square. We substitute that cos squared using the identity property of cos and sine. Now what you're going to end up is doing a chain rule. What's happened here is that's your function, let's say we call it u. If you differentiate u, hang on, how does it work out? That will be a polynomial. When we differentiate u, sorry, u will be the sine. Let me rephrase that. So u will be sine. When you differentiate u, that will give you cos. And by substituting, that cos will disappear, and that will give you a new integral in terms of u, which is a polynomial, and that will be easier to anti-differentiate. And then you will substitute u back by the sine of x. Okay? Yes, Josh, I was told before, and I can see that, and I will update the rule accordingly, and I have to do that now, otherwise I'll forget. Did somebody drop out? That's fine. It's just my WebEx flashing, and I'm trying to teach at the same time I keep an eye on the chat. Alright, so let's go to this substitution. So here you factorize cos x from that cos cube. We said u is sine of x. When you do du dx equals cos of x, what you can do here to add, we make dx, I'm going to make du the subject, like that. Okay, what it means is that cos s dx, which is up here, will become du. So now that cos x is getting absorbed into the du, and the 1 minus sine of x is become 1 minus u squared, and is just going to be a polynomial. Now just be careful now, we're working with the definite integral. So the definite integral means you have the boundaries here, a and b. So when you do a substitution, you also need to substitute the boundary. Okay, don't forget. So for example, if you start, the first boundary is pi on 2. If you substitute u, sine of pi on 2 will give me u equals 1, and when you substitute x by 3 pi on 2, because it's sine, that will give you negative 1. So what you will end up when you substitute and you only have u left, the boundaries here will change. So now that area is 1 minus u squared in terms of du. So notice the cos of x is completely gone, and what you end up with is you have your boundaries from 1 to negative 1. If you don't substitute that, your integral, your definite integral, is going to be wrong at the end. You substitute with square brackets by anti-differentiate. 1 becomes u squared becomes 1/3 of u cubed. Alright, you substitute the boundaries, so you do the difference. So that term is all of that function, and you substitute negative 1, and that one is all the same function, and you substitute 1. Because you have a minus, don't forget to add an additional bracket. Okay, otherwise you're gonna get that, you can make a mistake of the sign. So don't forget, when you expand, don't forget to have that bracket. So that would be negative 1. That negative and the negative gives you plus 1/3. Okay, you simplify that, that area is 4 on 3, and it's positive, and that's a good sign. Alright, so that was 8a. So it's the application of the fundamental theorem of calculus, is to find the area of a curve. It's one function. Okay, now the extension of that is with 8b we want to find the area of a region between two curves. Okay, so graphically, let's say you have something like this. You have a function f which is above the function g, so in blue. So you have the situation when f is greater than g along that interval a to b. So a and b are your boundaries. A is less than b. You find out that to find the area between the two curves, what you can do is the integral the area of f. So when you do the integral of f from a to b, you calculate the whole area of the red curve to the x-axis, and then you minus the area of g, which is that area below. When you do the difference, what you cut, the difference between the two will give you the area between the two curves. Because the boundaries are the same, we can regroup that into one integral, and the new function is going to be the difference of the two functions. So this is what's important, is to simplify your calculations, is you do the difference of the function, you anti-differentiate, and you use the boundaries. Okay, so most of the time that expression is not going to be the most accurate or effective method to use. Now, not all the time your boundaries will be given a and b, so they will look at examples when you will have to actually determine your boundaries. So here, find the area of the region bounded by the parabola y equals x squared and the line y equals 2x. So notice this time the boundaries are not specified. So good idea to have a little bit of a graph, and you need to determine the boundaries. So the boundaries is when the two y's are equal. So you make x squared equals 2x. It's a quadratic equation, very easy to solve. That will give you two values, which will be your boundaries. Here, if you graph it, your straight line will be above. Now, it's not really a problem if it's above or below. Let's say you use a CAS calculator, you will use a modulus. I guess if you do it by hand, you need to have an idea if it's above or below. Yeah, that's fine. I just don't want to continue along that path. So you need to find the boundaries. So that starting point and that one. So you make the 2y equal. You bring it on the left hand side, you factorize, don't need to use a quadratic formula, you'll find out x equals 0 and x equals 2. So those are your two boundaries. I don't know what it's mentioning the coordinates. You don't really need that. Okay. Anyhow, to find the area, so it's an integral from 0 to 2. The function you have inside your integral will be the difference between the two. Because you know the straight line from the graph. Let's say from the graph you can see the 2x is greater, so you start with 2x and you take away your x squared. You anti-differentiate that. 2x is x squared is a third of x cubed. It's from 0 to 2 with your square bracket. And what you do is you substitute 2 into here, that gives you 4. You substitute, hang on, no, let me rephrase that. If I substitute 2, x squared becomes 4, the minus x cubed over 3 is negative 8 over 3, and then you minus that function by substituting 0, because they all have x terms, it cancels out. So what's left is 4 minus a third. That simplifies to 4 over 3, so that is the area in square units. Okay, again your integral is positive, so if it's by assuming that 2x is above x squared. If you do the other way around and you find out that it's negative, what you could do, and if you already know you have your intercept correctly, if you have taken the opposite and it's negative, by removing the sign, the negative sign, you can get the area as well. Okay. Alright, another example. So difference between two functions, they're both quadratics. Now it specified the boundaries, so the starting and end point. And let's graph that. Use a CAS to get an idea. Okay, so it's from -1 to 1. That's where the two lines are intercepting. The upside down parabola 4 minus x squared is above. That's the yellow curve. So you're going to do 4 minus x squared, take away the x squared plus 1 with the bracket. You simplify to a simple quadratic. You anti-differentiate as a polynomial function. You substitute the boundaries with 1 on the left hand side. You take away, you substitute the -1, that regroups at 14/3. Okay. Alright, another example, a little bit of variation this time. The boundaries are not specified. So again, you will need to make them equal to find where the curves are intercepting. Now, it's a bit trickier because now they're intercepting at 3 points. It's a cubic, so it can have a cubic. When you make those two equals, you end up with a cubic equation that gives you up to 3 unknowns, and indeed we have 3 intercepts. So if you do the integrals, you're gonna have let's say if you do the integral of the blue curve, take away the red curve, you notice this one's going to be positive and this one's going to be negative. So they're going to be different signs. So when you find the area, what you need to do is you anti-differentiate between separate boundaries. So you're going to have two separate integrals, and the negative integral, you will need to take the opposite. Okay, so the way it's written down, so first you determine your intercepts. So you have the origin because we factorize x. You have a difference of two squares that give you positive and -1. So you have -1 and 1. Okay, now you notice that your cubic is above from -1 to 1, but from 0 to 1 it's below. Okay, so when you do your integral from, you want to find the area, so from -1 to 0 we can do f minus g, but from 0 to 1 we're gonna have to do g minus f to find the area. You have to do the opposite. So it's f minus g from -1 to 0, and from 0 to 1 we have to do the opposite. As I said, it's g minus f. You substitute by the polynomial, you anti-differentiate, so they're going to be opposite functions. Okay, you substitute with the boundaries, you regroup, simplify, and you end up with 1/2. You can do that as well, that will work. So let's say you double it. So what you would do is you cross off that one, cross off that one, cross off that one, cross off that one, and you double off that, and that will give you your area. Okay, now just be careful with the doubling. You need to be certain that you have either an even or odd function when you do the difference. Okay, so that could be an extra step. In this situation it's simple enough that you can see that they are the same, but if you do the integral from -1 to 1 and split it into two integrals, you can't be wrong, for sure. Alright, on the CAS calculator it's so much quicker. So you can find your intercepts here by doing a solve function. you don't need to separate your integral to find the area. As I said before, you go from your start and end point, you ignore the zero. But what you do is when you do the difference of your function, you add a modulus. What it does, it will ignore when the difference is negative, it will flip it around, and you end up with the area as an answer. Much quicker on the CAS calculator. You don't have to worry about intermediate boundary of change or whether the functions are crossing over. Talking about crossing over, you get a situation. You have two functions, different period. Here it's a period of 2 pi and a period of pi. Because it has a shorter period, it will start intersecting right here. So when you find the area, you need to split it into two integrals. Before you split it between two integrals, you need to find that value, that boundary. You can't just anti-differentiate from 0 to pi on 2. You need to find that intercept where they are crossing over. And you can do that by hand. You have cos of x equals sine of 2x. Sine of 2x, you use a dual angle property. You bring it on the same side to make it equal 0. You factorize cos of x. Cos of x equals 0 gives you x equals pi on 2. Sine of x equals a half, it's pi on 6. Now you don't need to use the general formula because your interval is from 0 to pi on 2. Okay? So pi on 2 is your end boundary, so that's where it's intersecting, but the intersection here that you know here is pi on 6. Okay? So now what we can do is write the area. So here the blue curve, cos of x from 0 to pi on 6, cos of x is above. So you do cos of x minus sine of 2x. And from pi on 6 to pi on 2, you do the opposite. Okay? You anti-differentiate that, the opposite function. You substitute your boundaries. Okay? You expand your brackets, regroup the like terms, or simplify your fraction. That gives you 1 over 2. Okay? Use the CAS calculator to verify. Don't forget to use a modulus. Alright? And that's it. That's 8a and 8b.